I didn't need an explainer. I mean, everybody. I know. And I like maybe in the future I'll ask you again because yeah. Well, this charity. Government. Well, I hope so. She said at the beginning she doesn't wish us to. Me and my wife. I hope we will make it.
Okay, let's start the final talk of this morning's session. It's going to be given by Eugene Bogomolny on spectral statistics of a pseudo-integrable map.
Thank you. First of all, I would like to thank organizer for inviting me. I will not discuss the graphs. I will discuss something related with unitary matrices. In principle, it can be realized by graphs, but I don't see any reason to do it. So this paper that I have discussed is done in collaboration with Robbie Dubertrand and Charles Schmidt. Charles Schmidt unfortunately died last September, and not many people knows him because he was not he did not like to go to the conference, so I just show his portrait, and he works till the very end on different subjects. So what are pseudo-integrable map and why it's so interesting, how it's related in more general settings? You know well that there are chaotic systems, there are integrable systems. Less known that there are intermediate class of systems which are interesting from all points of view. It's called pseudo-integrable systems. And pseudo-integrable systems can be realized, for example, as two-dimensional billiard where all angles are rational with pi. And classical mechanics and pseudo-integrable billiards can be reduced to what is called interval exchange map. For example, imagine that you have a triangle like this, and you consider trajectory going in this direction. When it hit this boundary, it should be go back, but we continue it to unfolding, and then it jump it from another side because this path should be identified. And you see that finally all points of these intervals will be here, and the boundary of the intervals are lines which are go to the singular corner, either here, either to this corner. And if you look carefully, you will see that finally you have interval exchange map. It means that you have an interval, for example 0, 1, divided in n subintervals, and you apply special permutation and so you have this classical mechanics. Much less is known about quantum systems, so there are a lot of numerics, but much less stably known. I will consider in this today something related with the simplest possible interval exchange map. So I have two intervals, I just interchange them. In these integrals, this map can be realized in some sense by area preserving map of coordinates and momenta as linear as the superposition of two transformations. One of them is a very simple transformation. You just shift x by a certain function of p, and this is a map, and model 1. And second, you shift p by a constant and did not change x. And if you do both, you have something very simply looking. And to me, as I told you, in general, for general alpha, this map is just parabolic. But I am interested here for pseudo-integrable map when alpha is rational. Alpha is m over q. And in this case, it's easy to see that q's power of the map will not change p, but x will change x plus constant, a certain constant. And if you consider this transformation model of 1, you see that these intervals, after adding a constant, goes to this direct, to this plus, these intervals to go to the first plus, and so it's really interchange of two intervals, the most simply possible. how one can compute quantized version of this. What means quantization? Quantization means that for each classical map, I attribute a unitary matrix whose saddle points in some sense corresponds to the classical equation of motion. Of course, it's not unique, but so you need to choose some transformation in some relations to this map. And it was done like this. You quantized, first of all, transformation of phi, where you did not change the momenta and you change only coordinates, and then you can easily convince you that this finite matrix k equals 0 n minus 1, where f is related with the derivative of f is function if, corresponds to unitary matrix whose saddle points give you classical transformation. So it's just simplest possible unitary matrix where you know all eigenfunctions, all eigenvalues. But slightly more complicated is quantization of shifting in momenta. And why it's more complicated? Finally, I will use this matrix, q prime q exponent 2 pi alpha q. And it's more complicated because usually when you're working on the tori modulo 1, all functions should be periodic modulo 1. But this function is not periodic. When I add q plus n, it changes. And this explains that before mathematicians which do this one, it was Zeev, Rudnik, and Jens Markov, they proposed to use a different type of quantization where alpha was approximated for each n in rational of m, and it leads to very nice mathematical formulas, but from the physical point of view, it had no big sense. And this poor man quantization leads to very interesting results. In all cases, this is unitary matrix, and so the product will be also unitary matrix. And my main object will be this simply looking matrices. It's a product of two unitary matrices, and it was done by Olivier Giraud, Jens Markov, O'Keefe in 1994, and they consider a particular case where phi is equal k squared. I did not like this case because it's two number theoretical. And finally, I will compute arbitrary phi here, even random phases. And if you do Fourier transformation of this matrix, you obtain another unitary matrix. You may not see that it's unitary, but you can believe it that it will be unitary of dimensions n, where this phi k will be random phases. I will speak slightly later. And only one parameter. You have in really two parameters, n dimensions of the matrices, and alpha is a constant, rational constant, which I will use rational or irrational. It's up to now it's irrelevant. It's a finite unitary matrix, which looks like any matrix of quantum graphs. You have diagonal matrices times a constant matrices, constant unitary matrices of a very special form. And I will consider two cases. First of all, cases where all phases are identically distributed random variable, independent random variable between 0 and 2 pi. And second, cases where elements related by symmetry are exactly the same. So you have only not before, in this case, you have n random variables. In this case, you have roughly n minus n over 2 random variables, and by the symmetry, they are equal. So this is my object, which I like to consider. And what I'm interested in mostly of the spectral properties of this matrix. It's very simply looking matrices, and spectral investigation of ensemble of random matrices, it goes to Wigner and Dyson, and it's for quite a while. So it looks quite innocently looking matrices. Just before I go to the result, I will show a few numerics. If you choose alpha irrational, say square root of 5 over 2, and you compute symmetric matrices, it is this guy. In non-symmetric matrices, it is this guy, and you see that nothing very strange appears. It looks like a normal random matrices. Solid lines, it's a Wigner surmise for random matrices. It looks like normal, which explains the name which I have attributed for symmetric case, GOE analogy, Gaussian orthogonal ensemble. For non-symmetric GUE, Gaussian unitary ensemble. So it's practically every random matrices which you have in mind looks like this, so it's maybe quite difficult to prove that it's really random matrices, but at least it looks quite natural. The situation changed drastically when I choose a rational alpha. Let's imagine that alpha is 1 over 20. And then here there are two plots, one a plot of n equal 801, and second is 809, smoothed over 100 realization. And you see something unusual coming. When n is 809, you see this curve, and this is together with the Wigner ansatz, Wigner surmise for unitary case, and you see that it's quite close. I will show you later that it's not random matrices, but it's some another forms, but nevertheless nothing too interesting happens. On the other hand, when n is equal 801, it's not, you see that completely changed statistics. And this is a formula which I will discuss later, that it has to be described by s power 19 e minus 20s. So you have here extremely strong level repulsion, and then it follows completely different behavior from any standard random matrix ensembles. The same story appears for rational, for symmetric matrices, where only half of coefficients are independent. And you see when n is, for example, 803, it is practically undistinguishable from standard random matrix ensemble, though, as I told you, it is not random matrix ensemble. But when n changes very little, 801, you see completely different behavior. And this is the main story which I would like to discuss today, how one can explain this and similar behavior. So my main results will be the following. The most interesting and most spectacular results from my point of view, when alpha is rational and m numerator times n equal plus minus 1 modulo q. This is the most interesting case, because in this case I will show you that its statistics coincide with which is called by jargon semi-Poisson statistics, which are defined by one parameter beta equal either q minus 1, either 1 over 2 q minus 2, correspondingly for non-symmetric and for symmetric matrices. In semi-Poisson statistics we have considered some years ago, it was just a completely ad hoc invention. You know, in standard random matrix statistics, probability of having n energy labels is just product of all a difference between energy labels. But in semi-Poisson statistics, for some reason, we have considered products only of nearest neighbors. So you have ordered sequences, and you plot the difference only nearest neighbors and put into the power beta. And for this case, you can compute everything, and it was not random matrix, it was some kind of models of, which is called intermediate statistics. But nevertheless, it's by strange miracles appear here that here you have exactly these statistics when this condition is fulfilled. This condition is quite important. If this condition is not fulfilled, some another R modulo Q, I will show you how to construct explicit formula for all correlation function by using transfer matrix approach. So everything is under control, but the most interesting case, this one, because in this case, you have a very simple formula, a quite unusual formula. For example, nearest neighbor distribution. It means that probabilities and two labels going closest to each other by the distance s is s power beta. But I told you beta can, depending on alpha, beta can take any integer or half integer value. And you can compute two-point correlation function explicitly. You can compute which is called label compressibility, which is important characteristic of X spectra. For all random matrix ensemble, key equals 0, but here the key value for a factor of 0 is non-zero value. So in this case, everything is under control. It was quite strange because for many years we have learned that only in random matrix ensemble appear only 3 value of label repulsion. This phenomena, that probability of labels goes to 0 when S goes to 0, called label repulsion, because labels are not completely independent. They fill each other, and it was a work of Dyson, so only 3 value can appear dependent of the symmetry. Beta equal 1, 2, and 4. But in this case, though we have some completely strange, completely natural random ensemble, here you can have arbitrary integer or half integer value of beta. And so this case fit what which is called intermediate statistics, which has a property that P of S goes to 0 when S goes to 0, S power beta, but the tail of for the large distance is a linear in S, and not as random matrices. You have S squared, and also for all intermediate statistics, one have to have that, which is called number variance, some correlation functions grows linear with L, and this parameter is also differs for random matrices and non-correlated sequences, and here it takes some intermediate value, which explains the name of intermediate statistics. Just to show you that it's not completely nonsense, I will show you just some numerics for alpha 1/3, 1/6, 1/9, and for non-symmetric matrices. And I told you that this power should be denominator minus 1. So alpha 1/3 you should have S squared, alpha 1/6 you should have S5, 1/8. And you see very nicely it's agree. This is a squared, this is a 5 power, this is the 8th power, and this formula, and this is just normalization constant, which I have showed you before. It's not interesting, and it is without any fitting parameter. You go quite nicely for this guy.
How do you compute the spectrum? You take random phases and then...
For sure, you have, I told you, we have 100 for, you take random phases, you diagonalize the matrix, and use, then have 100 realization of these processes, and you plot nearest neighbor statistics. Here you have 2-point correlation function examples. As I told you, everything is known here, and correlation function has strange form, but nevertheless for integer beta it can be expressed very easily. And you see very nicely agree with what you can imagine for semi-Poisson statistics. So it's first time realization, the same for symmetric matrices. Here you have even strange behavior, square root of S in the origin, and you see that numeric square root 3/2, 5/2 in numerics fit quite well to everything which we know, which we can compute. So now I will try to explain how one can get these results. And these results will be based on 2 facts, 2 main steps. If alpha is rational, say for simplicity I would consider 1/q, but everything can be done for m/q. The matrix m power q, so I have my initial matrix, and which has very strange statistics. But the matrix m power q, when I put in the q's power, will have Poisson distribution for all q and n. This is a first statement, and how it's possible that matrix M have not very non-trivial statistics, but matrix M power Q has Poisson statistics. It's really like this. Imagine, because of M is unitary matrix, all eigenvalue of unitary matrix are lying on the unit circle. So let 1, 2, 3, 4 I close by eigenvalue of matrix L. If I put to some power of matrix M, say M power Q, cube, then this guy will go to some other place. This guy will be 3 times farther from this guy, but all other guy will go here, because there is you have here eigenvalues, so these eigenvalues, when I put it modulo of cube modulo 2 pi, will be in between. And the main property which is important for everything here is a strange property that when n is equal plus minus 1 modulo q, in m power q, between any 2 labels which were close by in M, there is exactly q minus 1 labels which are going from around the circle. So if alpha is 1/3 as here in M power q, then I know that if I follow 2 labels, 1 and 2, which are here, I will know that in between will be two new labels which are going from where, from here or from here. And this is between any two, I will have exactly q minus 1 label. And now you see immediately how everything fit very natural to this scheme. If it's, imagine that this is correct, that m power q has Poisson statistics, but to go to matrix M, I have to jump it exactly of the q's label. As in the example before, I should skip two labels here and consider these labels as a representative of labels of m power q. And if you do it, then it's very easy to see that it's a semi-Poisson distribution with beta equal q minus 1, exactly as I told you. So these two steps, if you succeed in to prove, you can obtain very natural that m power q have very simple statistics. In this case, Poisson, for symmetric matrices, it will be a different statistics, but also universal. But M matrix has completely a different behavior. So sketch of first step one, but I told you, from physical point of view, it is quite natural that m power q have Poisson statistics. Why? Because, as I told you, if I have a phi alpha, my initial map, classical map, phi alpha squared will be p plus 2 alpha or some sum. If I put it to the power q, I will have p plus q alpha modulo 1. But if alpha is 1 over q or m power q, q alpha modulo 1 is 0. And so when alpha is m over q, q's power of classical map is have conserved momenta. In general consideration, if you have conserved momenta, it means that you have additional integral of motion, you have integrable map. And so it's quite natural that m power q as any integrable map should be Poisson statistics. In this case, one can do it by perturbation series of n, but I was slightly lazy to do it tedious estimate how to prove it really mathematically. So this part you should believe on physical intuition or do it yourself, because I think it is a theorem, but it should be done and I don't have time to do it. But if you do perturbation theory, you can easily see that m power q has a nice spectrum, and then you should estimate terms of perturbation theory as usually in the it is transition between quantum and classical mechanics in some sense. So for sure I know that it have to work, but it's not so fun to do it. Just to show that it's really correct, I plot the same eigenvalues as before, 1/3, 1/6, 1/9, but considering their q lambda on the unit circle, and this is a prediction of Poisson statistics, and I shift it, and you see that nothing changes. It's the same Poisson statistics everywhere, and we have checked it very carefully that for all cases it's very nice Poisson statistics. So let's assume that this is correct, and then I will prove you, to my point of view, less trivial stuff, that after q iteration you will have, after m power q, between any two close by will be exactly q minus 1 eigenvalues. And this, what I will prove just now, that for any alpha in n, let's theta 1 and theta 2 are two nearby eigenphases, theta 1 and of m. Then exists another one, there is one eigenphase theta of matrix M, which are quite far from this one, and in theta 1, such that when I add 2 pi alpha, I will come exactly in between two of them, and if I subtract from theta prime tap 2 pi alpha, I will get exactly between two of them. This property is quite strange because it means that all labels are very correlated. If I put two labels, theta 1 and theta 2, very close to each other, some other eigenvalue should know that they have to come back after finite translation. But it can be proved by the following arguments. Assume that UKN be eigenfunction of M, a lambda are corresponding eigenvalues. It's just definition of my M. So I told you that I consider my matrix M was the same matrix but without this term. And now I add this term. So I have new matrix NKP, and easy to see that eigenvalue and eigenfunction of this new matrix are related to other one by simple formula. So eigenfunctions are 2 pi k over n times this one, and eigenvalues are just lambda n, some other guy, times 2 pi alpha. It's just a simple transformation. What is important here is that if I subtract 1 and add 1, I will get that NKP equal my original matrix plus another perturbation, which is a rank 1 perturbation. You see, it depends only of k, it does not depend of p. And this is a rank 1 perturbation, and it's well known, it can be checked in this case, that for one rank perturbation, eigenvalue of perturbed matrices are always in between eigenvalues of original matrices. I think it's known, but if not, I can show you how to do it, but it needs some transformations, and I try to avoid it. So main step here is that there exists some other matrix which is a rank 1 perturbation of original matrices in such a way that I do know eigenvalue of perturbed matrices. But as I told you, because for any rank 1 perturbation, these eigenvalues or eigenphases should be in between eigenphases of the old one, it gives you exactly this lemma which I told you before. So what it means, just one pictorially. So imagine that I have this lemma is the following, that if I have two eigenvalues of matrix n, then I know for sure there is one and only one eigenvalue somewhere in the spectrum, also of matrix M, which after translation will be in between these two. And inner translation will be in between in opposite direction. And it is this property which is crucial, and it's valid for all alpha, rationally rational, and for all n, it's not related for anything, for any number theoretical guy. So it's a long-range correlation. It's a very long range because these eigenvalues knows about these eigenvalues and all other of them. And it is valid for all intervals. So here I know that some other intervals will come here. And it is this property which is important to prove, which is important to, and this is a theorem or lemma, that it's valid here. Another importance, at least for when mn is equal plus minus 1 modulo q, as I told you, this long-range correlation will be transformed to a very short one. Then I will prove just now that in m power q between any two nearby labels from m, there exist exactly q minus 1 new labels which appear after rotation. To prove it, I need to do some geometry. First of all, I will split the circle in the q sector of alpha 2 pi over alpha, 2 pi over q when alpha is 1 over q. And I will denote it, so all eigenvalues of matrix M will be somewhere in each sectors. So I will denote the distance from this sector anti-clockwise direction as xk, and opposite clockwise direction as yk. So this is a xk, this is a yk, this is a xk plus 1, yk plus 1, and also, so it's just notations. And then follow the property. As I told you, here I have interval between two labels. As I told you, there should be only one eigenvalue which have to be coming after rotation by 2 pi alpha, plus minus 2 pi alpha. But it can be only either it is this one, either it is this one. All other are bigger. You just simply see it from geometry because the angle is 2 pi alpha. So only either this will go this way or this will go this way. How I can do it? If this distance is smaller than this distance, then it is this guy which should be here. So if yk plus 1 minus yk is less than 1k, then after rotation it will be here, and it means that this guy I cannot come here. It means that xk plus 1 should be bigger than xk. So if it's follow, then this one. If in opposite, this guy have to come here. So yk plus 1 bigger than yk, then it means that xk plus 1 should come here. So either this guy go this way and this guy go this way, or opposite. And for all k, it means that the product of of these two distances, clockwise, anti-clockwise, is always negative. So this is the first relation which I will need. And second, I need relations of which connected number of points in each sector. So let's nk is a number of eigenvalue of matrix M in the sector k. Nk plus 1 will be number of eigenvalues in sector k plus 1, and so on. And now you can, if you think a little, you will see that all in between labels should come from this guy. The only possibility, you should have either xk plus 1, this guy will go here, and then it's just a matter of simple reasoning. Who will go to what? Who will go here? Either this guy go here and no one label here, or there is another label here, and in this case it have to come somewhere here. And if you do it, you will easily see that you have recursive relations that nk plus 1, nk minus 1 plus Heaviside theta function, which is equal 1 when this argument is positive, or 0 when it's negative, and this one. And because of these two guys are of opposite side, you see, here it should be this one, you see final recursive relation which I will use is like this, that nk plus 1 equal nk minus 1 plus xk minus k plus 1 plus xk plus 2, which are here, minus xk plus 1. It is just something which easy to, when you play a little, you do it. And now I will coincide, before it was arbitrary sector, and now I will coincide my division with a point y equals 0. I will put line like this, just for convenience. And then you see, first of all, that x2 is always x1, and also xq less than x1, which means that it is this one which goes to these intervals. And then you have chain of inequalities, n2 equal, as I told you, like this. And this is always negative, so it's 0. So it have n1 plus nx3 minus x2. n3, it should be valid for all intervals, all sectors. So you have n2 plus the theta functions, and you put it here, and you put this formula here, and you see here it's appear x3 minus x2, x2 minus x3, so the thumb is always 1, and you follow, and you get this relation, and you continue this relation, and finally relation like this. So you have nk is equal n1 plus theta k plus 1 minus xk, and so on. You play this game, and you find total number of n. Total number of n is n1 plus n2 plus nq. And so you have nq plus, it's equal, you have q terms, q n1 plus 1 plus the sum of q minus 1 theta function. And now you see something very nicely. Imagine that n is 1 modular q. If it's 1 modular q, the only way that in this formula it's possible that all theta functions should be 0, which means that xk should be less than xk minus 1, should be less, and so on, less than x2, less than x1. And this is exactly what I told you, because when I put m power q, the xq and xq plus 1 are differs by 2 pi alpha, 2 pi over q. When I put it power q, they will differ by 2 pi, so which means that they are 0. And it means that between two eigenvalues, x1 was the difference between two close by eigenvalues of matrix M, you have exactly q minus 1 other eigenvalues which are coming from all sectors together. When q is equal minus 1 modulo n, you also see that it's only possible when all theta functions are 1. So you have also a chain of inequality in different orders, and so it's the same story. Between in interval x1, you have all other labels which are coming exactly in this interval. And so you prove this lemma. And if you combine together these two steps for non-symmetric matrices, then you see that two statements together, that non-symmetric matrices eigenface of m power q are Poissonian, and it is valid for all alpha, for all n. It has nothing to do with n. But if n is equal 1, then you have to obtain from m power q eigenvalue of matrix M, you can jump it from q minus 1, and you see that it's immediately statistically semi-Poisson with beta equal q minus 1. So this is a very strange property. Nevertheless, I continue, some miracles continue for symmetric matrices. Up to now, I told you that it's non-symmetric matrices. For symmetric matrices, if you argue something physically, you will see, you see that for m power q, you also have universal statistics. It means that for all alpha, for all n, for all rational alpha m over q, m power q is universal, but not Poissonian, and it forms another sequences which is by absence of a name I call super Poissonian. In super Poissonian is a statistics is a square root of Poisson statistics. What it means that if I have Poisson statistics, if I have two labels independent, and super Poisson, if probability of products I put somewhere inside that two label probability of when I jump to two labels are Poisson. So you have this type of relations, and you can easily convince yourself that this can be solved immediately, and you see that it's once more semi-Poisson with completely unusual value of beta equal minus 1/2. So for m power q symmetric matrices, instead of label repulsion, you have label attraction of s equal 1/2. And just to show you that it's not contradict numerics, you have alpha 1/2, 1/3, 1/5, 1/7, and it's the same value which I showed you before, quite constrained functions. Nevertheless, if you plot m power q, you see that it's fitted. I shifted in this direction, so it's a 1/2, 1/3, 1/5, and 1/7, and you see that it goes have singularity, square root singularity, but of course it's integrable. It's very nicely fitted to this guy. Everything we have checked is okay with this. So it means that if you accept this point of view, you can compute spectral statistics for this particular value of n. It means that n equal plus minus 1 modulo q. Less known about wave functions, and from general physical consideration, it follows that every time you have intermediate statistics, you should have fractal or multifractal wave functions. Just to check numerically, unfortunately, we have compute participation ratio. It is a moment of case to k power minus 1 inverse participation ratio. You do normalized, and it is if it's fractal or non-fractal, then when n goes to infinity, this quantity should be n power some power dk, and which depends of k, and dk one can write d small k times k minus 1, because this is a normalization of this guy. And if it's this quantity are not 0, if they are 0, it means that the eigenvalues are localized. If they are 1, it means that eigenvalues are delocalized. So it is some kind of measure of fractality of this set. And if you do numerics, you see that its value is quite nicely not standard, which confirms, at least in this form, that they have fractal statistics. I hope that it can be done analytically, because in this field there are some unusual relations which you can derive. So this unusual relations that means that lambda, if lambda and U are eigenvalues of matrix M and normalized, then the unusual relation for this quantity. If I have a mean value of all indices K for the eigenvalue M and the same multiplied by 2 pi Kn, the same guy, you see one can prove analytically that modulus of this guy are related only with lambda of eigenvalue of lambda. It is real, but I did not have, don't need it to show it. So this is in the opposite relation for this guy where alpha is changed to minus alpha. The existence of this relation in some sense says that if I know statistics of lambda, which I suppose to do, I can compute some kind of non-trivial property of function M, but also I did not investigate a lot of this guy. Another predictions which I showed you before, it is the existence of short-range correlation. This is exactly the same 1 point alpha. But I told you, when you go further and further, finally the labels which are very far should know they have to come here. And it really shows you in different scales the same function. Here you have this complicated function. Here you have some noise. And here you have big peaks, which shows that these labels are correlated exactly near the point where they should be. And then you have another peak and so forth. So now I will briefly show you how one can compute spectral statistics when n is not equal plus minus 1 over q. And in this case, it appears that the best way of doing it, at least what I found, is using transfer matrix method. As I told you, I divide this the circle in q segments and have proved the existence of relations like this. And now I will put each segment I will put on the line. So instead of q sectors, I will have q lines. So this is for alpha equal 1/5, I have 5 lines. And this is exactly the eigenvalues which were in the sectors on this line. Why it's interesting? Because, as I told you, for n equal 4, which is minus 1 modulo q, you see that all theta function has to be equal. It means that these relations are fulfilled. And it's nice to put graphically this relation x2 bigger than 0, less than x1. x3 should be somewhere here, but bigger than x2, x4. In x5 should be somewhere here because it's less than x1. And x1, it's the position between nearby labels. And it is this guy appear, and you see how it's related. Between these two labels, you have another one which are shifted by 2 pi over q because it corresponds really, it comes here. Between these two labels, you have another guy. Between these two labels, you have another guy, and so forth. And it is exactly the case which I have investigated before. But it was based on inequality of theta functions, that all theta functions have to be equal 1, otherwise it will be not correct total number of points. But if, imagine that n equals 3 modulo 5. In this case, only 2 theta functions have to be equals. It means that if before they were very attributed, now in this sector, they have to be plus, plus, and 1 minus, and 1 plus. It should be like this. And if you use another relation, you will see that another sector, it should be somewhere, but follow the same pictures. On playing a little, you will see that it's always possible to put, to connect it in some a different manner, to connect it like this. Before you connect this y with this point, and now you connect this point with with this point. And all these lines should be not intersect each other. So the difference between previous case, which were here, that here labels should be connected each other in not intersect, but not intersection was trivial because they are in different sectors. And now points are connected with a shifting by one. And if you play a little, if it is a higher Q, it will be shifted by some kind of k minus 1 sectors. So let's consider in detail this guy, how one can compute this guy. So what you need to compute? You need to compute your fixed eigenvalues which are close by in M, and you are not interested in what is going with all other eigenvalues. And now you see, I put here the block, and now you see that each blocks are defined when they show, when it enters, when lines enter, and when lines go out. Here the lines enter 2, line go 2, and then I can integrate everything in it, because of course imposing the condition of not intersection, which I will do it. But all other sectors are not involved. So I can split it separately. It's exactly what is called transfer matrix. And in this case, transfer matrix is 3 by 3 matrix, which corresponds, it can enter here and goes the opposite way. So, for example, M11 matrix is you go 1 and you go 4, and you should integrate over all Poissonian distribution, because here the matrix is Poissonian, M power Q. And if you play a little, you see that the only need what you to know, you need to know how many times there are ordered sequences. For example, I can put 1, 4, 2, 3, because I can put 4 here, but I cannot put label 4 here. So I have 1, 4, 2, 3. Then I can 1, 2, 4, 3, and 1, 2, 3, 4. You have 3 sequences, and each ordered sequences give you x power 4 divided by 4 factorial. And this is for M11. Here you have M12. If you play, you see that you have 5 possibilities, so the factor 5. Here you have 1 enters, 3 goes out. You have here 6 points, so you will have x power 6 over 6 factorial. And if you play, you see that you have 5 different indices, and so it's the factor of 5. You do it, and finally you see that when n equal plus minus 2 modulo 5, your transfer matrix is like this: 3 times xn e minus x, 4, and so on. Just some quantity. And if you play a little for symmetric matrices, you see that it's exactly the same formula, except that pi over n is a correlation function of Poisson processes. But for symmetric matrices, you have super Poisson processes, and the corresponding nearest neighbor n correlations are given by this formula. So the difference between symmetric and unsymmetric that you have here only this quantity. Then you play the game, for example, for n alpha equal 1, 7. When n equal 5 modulo q, you see that you should do the same type of construction, and so you have transfer matrix, which is a 5 by 5. Any line can enter and any line can go out, so you have 5 by 5 matrices, and when you compute, you have some numbers like this. For n equal alpha 1, 7, n equal 4, you see another picture appear, because now if you look carefully, you should come not this point, but 1 point later. And so if you separate one block, you see you have 2 enter lines and 2 outside lines. And here you have 5 blocks, so you have 10 by 10 matrices, which should appear as a transfer matrix. It's slightly more tedious, and this is an example of this n equal 4 matrices. You should put it in this way, but I don't have places. So you can compute transfer matrices. But what is useful? What is useful of transfer matrices? Because if you see, and for this problem, you easily see that probability of having n labels, x1, the difference x1, xn, is just a trace of all transfer matrices are of this value. And if you know this, you can compute everything by hand, because it's very easy to compute all correlation. You can easily integrate over all one xn, because it's a linear form, so you integrate, you obtain integrated matrices, and you play a little, you need to compute Laplace transform to be 100% sure, and you do something. And finally, you get that in the limit of large n, because here you have trace large n limit, only the largest eigenvalue of matrix, integrated matrix, appear. And this is lambda is largest eigenvalue, so I have left eigenvectors and right eigenvectors, and you play a little, and you will find that you can compute all correlation function explicitly. In particular, the distribution of nearest neighbors are just m over x weighted with two vectors corresponding to largest eigenvalues is for their normalization e minus s. And you do this for these matrices. For alpha equal 1/5, you do for these matrices, and you see that P of s is equal polynomial of s squared, s cubed, s4, s5, s6. But it's not a series, it's just a finite polynomial, e minus 5s. And here you have some numbers which appear from diagonalization of these matrices. For symmetric matrices, you see that it starts from square root of s, ending of s5 over 2. It's also finite polynomial by the certain coefficients. Then you consider alpha 1/7 plus minus 2. You have higher order polynomial, but finite polynomial. And then you play a little, and you have for all these guys, it's just numeric. You should compute numerically this largest eigenvalue, but of constant matrices. But everything is here under control, and you do it everywhere. Finally, you compare with statistics. For example, for alpha 1/5 and n equal 802, this is a numerical computation of direct statistics, and line corresponds to one of the formula which I showed you before. When you do integrated nearest neighbor, you don't see any difference, it's just integrated nearest neighbor. So it looks like random matrix, but it is not random matrix, it's just finite polynomial. You do for symmetric, you see nicely agreement with the formula and so on. So finally, I would like to finish, and to conclusion. My conclusion is that very simply quantization of pseudo-integrable map seems to be a new class of spectral statistics, but I told you that I know only one example of this class, the map which I discussed, and I don't know other classes, other examples of this phenomena. For alpha rational, n plus minus q, this statistics is characterized, it is the most interesting case, integer or half integer level repulsion. And level compressibility is non-zero in all cases. And eigenphases of m power q for non-symmetric matrices form Poisson sequences. For symmetric, they form which is called super Poisson sequences. And so you can compute explicit, in some sense, everything here is a first explicit realization of random metrics which obey semi-Poisson statistics, and everything which you want except of fractal dimensions. But to my knowledge, no fractal dimensions till yet was computed analytically. Still, I am not completely, will be surprised that here it's possible, because there are some non-trivial relations. Eigenfunctions have multifractal property, non-computed analytically. It's open many questions, and it will be quite nice to continue this game. Thank you.
Are there any questions or comments?
In view of the talk that will follow after the lunch, if you have this unitary matrix, and if you take values of the elements of the matrix, take modulus square, and compute the spectrum, how does it behave?
Then, as shown in this Jens paper, then you have, it depends very strongly of factorization of n of number of prime numbers, because you have a Gauss sum, and a Gauss sum with random phases is square root of n with some coefficient evident. Here, instead of random phases, you have a Gauss sum which is a two reminiscent of number theory, and you don't have also statistics you cannot integrate. You can, it looks for special value of n, it looks quite similar. For special value, which are not factorized of primes, if n have prime divisors, Gauss sum have special property, because it's two number theoretical, and this is what I wanted to avoid. Still, I cannot avoid completely, because the answer depends of n modular q. And this is a difference, but it's a innocent, because I can do statistics for, I can go to infinity by this value of n. It's not nothing changed. When it started to depend of prime factors, I said it's too much to be attributed a name of random matrix ensemble. It's similar, but not exactly the same.
Yes. You use matrices for which the phases were really random independent numbers.
Yes.
You do the numerics also by taking a fixed function phi and taking phases which are n times phi.
What I know is that even if you put e k squared and coefficients, say, irrational, you will have practically random phases. It's a theorem in some sense. If you put k power 4, so you also will kill number theory, at least. But we did not do any numerics particular for special value of k. We did for some other reason, for different value of k, and then it's a different answer.
Do you have any physical models where you could apply this result to?
What you mean?
Example,
What you mean
any-
arithmetical
For
models?
example, the usual random matrix theory is applied to, it has been applied in nuclear physics to look for eigenvalues that are missing when you find eigenvalues of certain Hamiltonian in the nuclei, and that has been very effective. And do you have a similar physical context where you think you could apply this to?
Yeah. As I told you, we start, and we did before, a lot of computation for triangular billiards. This is a case where you have no, random matrices can be applied for chaotic systems, or integrable system obey Poisson statistics. Triangular billiards, like I showed you before, they have a property which are here, intermediate statistics. What was computed till now, strictly speaking, mathematically, was computed for triangular billiard the value of kappa for a factor of 0. It have been using for special type of triangular billiard which are called Witch polygons, where everything is under control. You know formula for number of periodic orbits. For generic triangular billiards, the situations, even with rational angles, situation is less clear. Even numerically, it's a bit difficult to have a judgment. So all this result applied, as I told you, for simplest triangular billiard like this. You have billiards at least for the angle pi, right triangle with angle pi over n. It's in which class? And for this case, numerics suggests that you do have new ensemble of random statistics, and it suggests that it belongs to intermediate class. But to do something, this was the reason why we consider maps like this, because they are simple, much more simpler than before. Still, they have completely unusual behavior, which stress one more that every time you have pseudo-integrable behavior, something happens. So results which I showed you before were initiated by investigation of example like this and different type of pseudo-integrable billiards. It's really billiards. It's not nuclear physics. I don't know any nuclear physics which obey this property. And also I don't know any quantum graph which I can attribute of pseudo-integrable graph. I know chaotic, I know integrables, But to my knowledge, it's not investigated what is a pseudo-integrable, how one can construct naturally, whatever it means, something with such properties.
How about the eigenstates of these triangle billets? Do you see fractal?
In phase space, of course. We did numerics, it is published somewhere. I can give you.
In some paper you wrote about, you studied superscarf eigenstates.
It's also related because it says superscar related. It's a billiard like this. It's a billiard, rectangular billiard, and you put in the center some slit. And the superscar is just manifestation of different properties of this guy. This explains, if you'd compute fractal dimension, you will see that they are fractals. But once more, we cannot compute analytically these fractal dimensions in this case.
Okay. Well, we should draw the discussion to a conclusion. Thank you again, Eugene. Thank you to all the speakers.